Hey guys, this is Sunny and my colleague Harsh, Qihuan, Tijas, Pari. So today we will present our work in the teacher-student creative learning. So from the research in reinforcement learning, we observed that the rewards are sparse for the learning model. And creative learning is one way to overcome the challenge for sparse rewards. So like human, we let the agents learn from easy tasks and proceed to harder tasks once easier are mastered. So to solve these challenges, we utilize a teacher-student framework to solve the problems. So the teacher is to monitor students' training process and select the task based on the difficulty for the students. And the student is trained for each subtask. And here we have n different subtasks. And in our experience settings for the games, we have different levels of games. And we utilize the absolute mean reward as our value functions to guide the student model to achieve the maximum values. So our contribution of this work is that we consider scalable subtasks. So since in the teacher-student creative learning, the experiment only utilize 5 different subtasks, so the action space for the proposed method is limited. And also, they evaluate this model in one evaluation task. So the limited subtasks will also have the overfitting problems. Nothing we want to do is to dynamic update the model structure of the student model. We want for difficult tasks, student model can change the structure of the proposed method by increasing number of parameters in the model. We set 2 different experiments to achieve this expansion. So before we move on to the detailed information of experiment, so let's first discuss what experiments look like. So now we utilize the games, 2 games, CoinRun and PackMan as our experiment environment. And the game instance take an action and return new state, revert, and the observation to the model. So the student model try to maximize the revert through the gradient ascent, and the teacher model select the subtasks like the level of games based on the revert difference from the beginning to the end. So in our first experiment, we utilize a CoinRun. So this game contains thousands of variant game environments, and it is harder for the model to overfit the environment. For here, we randomly choose 100 levels of games as subtasks and test the model on the unseen 10 levels of games. So we can see 100 is greater than 5 and 10 is greater than 1. And they evaluate the model without teacher-student creative learning and with teacher-student creative learning on the mean absolute reward per 100 time steps. So here we utilize the CNN model as the structure of the student model. So this is a result of the model with creative learning and without creative learning. So we can observe that when we include teacher creative learning, the model's performance got improved a lot. 22 is much greater than 0.4. And the teacher model can remember all stuffs. The second game that was tested was a game similar to PackMan that we created. The game board is a 10 times 10 grid board with 1 tile of food shown in green and some number of enemies shown in red and a player shown in blue. The goal of the player is to reach the food as fast as possible without touching the enemies. We implement different subtasks by varying the number of enemies in the game. The model evaluation was performed by running the student agent on a uniformly distributed set of 100 games. For the student agent, we use a deep Q-learning model, which is similar to Q-learning. In Q-learning, we generate a large Q's table with the expected future reward of taking each action from each state. And this table is updated after each step based on the step reward using the formula at the bottom. In the deep Q learning, We replace Q table with a neural network, and the updation is done through the backpropagation. For backpropagation, the predict value is a Q value prediction for each action from the neural network, and the ground truth is the learned value shown in the formula. Here is a figure of the mean reverse over episodes for two experiments, one without critical learning and the other with 4 different teacher-student critical algorithms. So in the first plot, as expected, the performance improves with more and more episodes. The fluctuation is due to the epsilon greedy policy. Since the epsilon decays over time, the fluctuation also decreases. In the second plot, we can see that reverse with most algorithms decrease before they increase. This is because initially the teacher generates highly biased probability distribution, causing overfitting. After more iterations, the models get to train with different subtasks and the performance improves. After discussing 2 experiments, let's move on to some limitations of our work. So in the teacher-student critical learning paper, the authors trained their model for about 2 million steps. And due to the limitation of computation resource, we only report the performance result of the first 10,000 steps. So this may cause the model unconverged in the complex game like CoinRun. And the conclusion for the whole project is that from our experiment results, we observe that teacher-student critical learning achieves better performance compared with the model without critical learning. And all the code is available at our GitHub website. From our future work, we plan to implement the progress model structures. In process game, it adds the convolution layer and the fully connected layer from the lower resolution to higher resolution pictures. In our example, we plan to add new fully connected layer from the simple game to the hard game. We finished most part of the coding, but there are still some bugs in the code that we cannot smoothly test our algorithms.